Hello, my name is Emma Underwood and I am a researcher at the University of California, Davis. I'm going to give the first of two talks on a post-fire restoration prioritization tool that's been developed for Chaparral shrublands. The second talk will be presented by Nicole Molinari, and she will be looking at the field validation of some of the outputs of the tool. So the fires that we are looking at in these two presentations occurred on the Angeles National Forest, the Copper fire that's in red that occurred in 2002, and also the Powerhouse fire that occurred in 2013, outlined in orange. So what we wanted to do was create a framework for resource managers on the national forests in these shrubland-dominated regions to be able to assess the regeneration capacity of chaparral post-fire, and also to predict areas of degradation, and finally to identify priorities for restoration. I'd like to acknowledge our collaborators from the University of Barcelona, Jose, Ramon and Beatriz. And these collaborators had developed a tool for looking at post-fire restoration in forests in Spain. And we adapted this tool to the shrublands of Southern California. The tool consists of 5 main steps. The first of all considers species information about the chaparral communities within the area of the fire. The second step considers the fire history, both the number of fires in the last 40 years, as well as the time since last fire. The third step considers drought conditions, both pre-fire and post-fire. And the fourth step considers non-native grass cover. Now, the output of those 4 steps provide us with a map of regeneration capacity of the shrubland within the fire perimeter. And we also include a 5th step for fires that have recently burned within the last 2 years, which is when the majority of most post-fire sediment erosion occurs. We include the risk of erosion, and this erosion risk data becomes combined with the map of regeneration capacity, and that integration results in a map of degradation risk. So the first step then is to determine the proportion of resprouting and facultative seeding species within the communities within the fire perimeter. So at one extreme, we've got obligate seeders that regenerate through fire-cued seeds. And then at the other end, we've got obligate resprouters that regenerate through new shoots. And then we also have facultative seeders that combine both strategies post-fire. So what I'll do is show you some screenshots of the tool and then show you how it runs. So the first step then is to define landscape units within the fire perimeter. So this can be done at 2 scales, either the core scale using the California Wildlife Habitat Relationships vegetation classes, or by using these classes which have been integrated with aspect, north and south, and also topography. So for example, if we looked at mixed chaparral, we have a south-facing slopes, summits and ridges category, which are the warmer, more exposed areas, often dominated by cedar species. And then we also have cooler areas, which would be the mixed chaparral, north-facing slopes, valleys and depressions, which are often more dominated by resprouting species. So once we've defined these landscape units, we can articulate the proportion of resprouted or facultative seeding species within each of these landscape units. So the user is presented with a default values, which are based on our work on the copper fire, but these can easily be modified using the pull down menu if based on field knowledge or expert opinion, the proportions are different for working on a different fire. And then based on those proportions, each pixel is then assigned a score So, for example, if it has over 40% resprouting or facultative seeding species, it's assigned 5 points. And what we can see in this map, output map 1, which is for the reflecting those allocations, we can see a large proportion of the copper fire is in that high regeneration capacity because it's dominated by resprouter and facultative seeder species. The next step is to modify that regeneration capacity based on the fire history. And the first step is to, we can specify the number of fires in the previous 40 years. Now, this is now an attribute of the FRID data set, so it's updated annually. So we can see parts of the copper fire, small parts are occurring in purple, which means it's had 3 fires in the last 40 years. And again, associated with those data is a point scoring system. So the points associated with each pixel within the fire perimeter will be modified based on the count of fires in the last 40 years. So, for example, in those purple pixels, the score for those pixels will be reduced by 2 points. We can also specify the time since last fire. And this is relevant for those pixels on the landscape that are dominated by cedar species. And this is based on the fact that it's often takes between 10 and 15 years before the seeds can accumulate sufficiently in the seed bank for post-fire regeneration. So we can see there are areas in dark red there that have had fire within the last 5 years. So the points associated with those pixels is reduced by 2 points. Now we can see the output from the fire history component of the tool. We can compare this to the upper left map, which is the previous output. And those areas which are circled in blue have experienced a change between the two. So the regeneration capacity has been downgraded from, in the terms of the green, from the dark green of high regeneration capacity to the lighter green, the moderate high, because of the fire history. The third step of the tool looks at the drought conditions, both pre-fire and post-fire. So in this screenshot, we're looking at the pre-fire conditions, and we are considering pixels that are dominated by resprouter or facultative seeder species. And this is because drought pre-fire can reduce the carbohydrate stores within the resprouter roots and can affect its ability to regenerate post-fire. So in this particular part of the tool, the user is taken to the NOAA website that looks at the Palmer Drought Severity Index by ecoregion, and the user is asked to calculate the number of months in the growing season from November to May that are classified as severe or extreme. And then the user enters this, and where the majority of those months are severe or extreme, then the points associated with that pixel are again reduced by 1 class. And there's also components for looking at drought post-fire and also the season of the fire. Step 4 of the tool looks at non-native grasses. And here we're using a data set developed by Isaac Parks based on the Landsat data that looked at the intra-annual difference in NDVI to try to identify herbaceous vegetation across Southern California, with the idea that much of this herbaceous vegetation is dominated by non-native annual grasses. So the user is able to specify a threshold. Above that threshold, it's considered the non-native species will affect the characteristics of the native shrubland. And again, we have a scoring system that affects the scores of those pixels. And this time we're looking at changing the scores of seeding dominated pixels, which are reduced by 1 class. So again, here we have the output from that step, output map 4, and we can compare this to the output from the previous step, and we can see that large orange area that is classified as Chamise redshank chaparral was moderate in terms of its regeneration capacity, and it's now been downgraded to moderate low based on the non-native species cover of those. So this is the output from the first 4 steps of the tool. We can see areas of low regeneration capacity, which could potentially be areas for restoration, occupy about 665 hectares or 9% of the copper fire. I just wanted to show you the last step for more recent fires, which is to integrate the erosion risk data. So the erosion risk data is developed as based on the burned area emergency response assessments that are conducted for fires on federal lands. And we've used the same class categories that were used in the Spanish tool. And then this soil erosion risk becomes integrated with the regeneration capacity data through a decision matrix, and the output is a degradation risk map. So areas in that map in dark red or red have very high or high degradation risk. So I'll just show you a little bit about how the tool looks. So it's written in a Jupyter notebook framework, and text in blue is text explaining the rationale for some of the decision rules. Here we have step 1, where the user can switch using the radio buttons between the course WHR vegetation type only compared to the vegetation type intersected with aspect and topography. And then here is the options for changing the proportion of resprouting and facultative seeding species based on those landscape units that have been identified. So for example, here the mixed chaparral south-facing slopes, summits and ridges could be modified from the default values that are based on the copper fire work to other values. And then by clicking the update tool, the following steps of the tool are rerun. And this is output 1, showing the reflecting that scoring system. And the download button can export that as a GeoTIFF that could be bought into a normal GIS package. Here's an example of where the user gets directed to the Palmer Drought Severity Index on the NOAA website and can modify the number of months that are severe or extreme drought. And those are tables associated with the decision rules for cedar and resprouter dominated pixels. And here we have the non-native grass component that for the copper fire, we used a 20% threshold, and you see the majority of the copper fire is purple. But if we change that to using a 50% threshold and update the tool, we can see that now a lower portion of the fire is now purple, less spatial area, and that has implications then on the output map. So we now see more speckling within that previously high regeneration area. And that's our final output map, as I explained, which we would proceed to do for fires that are within the last 2 years. So what we've done is to make the code for the tool readily accessible to the user, so that if certain things needed to be modified, for example, the scoring system might need to be modified if the tool is applied to shrublands outside of Southern California, then this can be done relatively easily. So the idea then is that the tool can be run on an individual's laptop with sort of basic sort of technical experience of it. And just to finish off then, I'd like to show just a couple of slides relating to how we can use those areas that have been identified as low regeneration sites. So they can be integrated with other data, for example, on ecosystem services. So here we've got data on runoff and recharge and biodiversity and biomass. In each of the cases, areas that are blue have higher values for each of those variables. And these data were compiled as part of a broader Southern California project. And what we did was for each of those variables, we scaled them and created deciles. And then we overlaid them. So we have areas in the map on the left, which are red, which have highest areas of ecosystem services, where there was 4 services occurring at once. And we can take these areas, these sort of hotspots for services, and then overlay them with the outputs from the post-fire restoration tool. And that can help us further refine areas for restoration on the ground. But we'd like to underline a critical component of this is the need for field validation of the outputs of the tool. And that's what we'll be hearing more about next with Nicole's talk. And before we go on to that, I would like to acknowledge the funding and also tremendous help from a whole range of people. Thank you.
Hi all, thank you for tuning in. I'm Nicole Molinari. I'm an ecologist for the U.S. Forest Service in Southern California. The majority of lands that I help manage are shrub dominated, and while chaparral shrublands are adapted to fire, they do exhibit signs of degradation and an inability to recover following wildfire. And the primary triggers for this include too frequent fire, drought, and the presence of non-native species. And because of the frequency and large scale of these fires, both we're living with at the moment, and the fact that they can be in remote and steep terrain, it's not always possible to get boots on the ground to evaluate recovery following wildfire. So these challenges have led the Forest Service to partner with UC Davis, UC Riverside, the National Fish and Wildlife Foundation, to develop a post-fire restoration prioritization tool. And we're calling this the PREP tool. And the PREP tool identifies and prioritizes shrublands in need of restoration following fire. So today, I'll focus on a field component where we set out to validate the outputs from the PREP tool on the Angeles National Forest. However, if you're interested in the tool development and more details about the mechanics of the tool, please tune into Emma Underwood's presentation, and it should precede this presentation. So a quick review of overview for those of you who haven't seen Emma's presentation, and review for those of you that have. So the PREP tool is a 5-step process that can be carried out on the post-fire landscape. And the tool essentially predicts regeneration capacity based on the species present in the pre-fire landscape, the fire history, which can be seen as step 2, drought conditions, both pre and post-fire, as well as step 4, which is non-native and herbaceous grass cover. So the regeneration capacity of the Powerhouse fire, so the map that you see is the fire scar from the Powerhouse. This is a fire that burned in 2013 on the Angeles, and it can be seen on the left-hand side of the screen. Just to get everyone on board here, the high regeneration capacity areas are shown in green, and these are areas we expect chaparral to recover to a pre-fire condition. The orange represents moderate regeneration capacity, yellow represents moderate to low regeneration capacity, and finally, the red areas represent shrublands that are predicted to have the lowest regeneration capacity, meaning they may be degraded and in need of restoration and some sort of human intervention. So we took the outputs from the tool into the field and set out to evaluate whether the predictions made by the tool were actually borne out on the ground. Basically, we wanted to know whether areas that were being predicted to have low regeneration capacity, those areas we just saw in red on the map, Were they indeed degraded and in need of restoration? Our second goal was to take a more detailed look at the effects of degradation on chaparral shrubs and their composition. We were most interested in whether shrubs that regenerate from seed, many of you know these as obligate cedars, whether these cedars were disproportionately effective when compared to species that can regenerate using a resprouting strategy. So the map on the top right corner is the same map you saw earlier, but now it's been populated with the plot locations. So the plots that we put onto this landscape can be seen as little black dots along the eastern edge of the fire scar. And a UC Riverside field crew set up 57 monitoring plots within the Powerhouse fire. Our original goal was to sample across vegetation type, aspect, slope, as well as regeneration capacity. However, due to issues with accessibility and the lack of certain vegetation crosses with regeneration types and slopes, the monitoring unfortunately was not fully factorial. So in the table at the bottom of the screen, you can see the distribution and number of replicates in each of the categories. So each of the monitoring locations consisted of a 30-meter point line intercept transect with a 30-meter belt. And so species cover and height were measured along the transect line, and shrub density was counted along the 30-meter by 1-meter belt. Our assumptions were that the areas that ranked in the lowest regeneration capacity classes, and remember these are the areas that we would predict to be degraded, that they would have the highest abundance of non-native grasses and herbs and the lowest cover and density of shrubs. We also hypothesized that seeding species would be less common in degraded areas because they're more sensitive to many of the stressors that were put into the model. These include fire history, non-native species abundance, as well as post-fire drought. All right, so let's look at some of the results. With respect to our first goal, which focused on evaluating the prep tool outputs, let me just get you familiarized with these graphs because there's going to be a series of them that all have the same axes. So on the x-axis, you can see these are the 4 regeneration capacity classes, and on the y-axis is the vegetation cover, and this is for grasses. And so with respect to grasses, we found that the cover of grasses was greatest in the lowest regeneration capacity class. So note the red bar here when compared to all other classes. So the non-native grasses made up the majority of cover in the low regeneration capacity class. And the most abundant species included Bromus diandrus, Bromus hortiaceus, and Avenas. You may notice that there is not a significant difference in the cover of annual grasses in the lowest and highest regeneration capacity classes. And I suspect that the similarity may be an artifact of the high regeneration capacity class being a mixed chaparral vegetation type. Remember, we weren't able to achieve that fully factorial design. And therefore, it has many species that regenerate from seed, as well as resprouters too. But the seeding component can be slower to recover when compared to resprouters. And this could be driving the pattern that we're seeing. Because shrub density is high in the highest regeneration capacity class, you haven't seen that yet, but you'll see it in just a minute, it's likely that the grasses will decline once the shrub canopy is formed, and there will not be a need for restoration in areas predicted to have high regeneration capacity. So if we move on, the herbaceous species follow suit with the grasses, such that the lowest regeneration capacity class, again shown in red, has the highest cover of herbs. And the dominant herbs consisted of both natives and non-natives. In terms of the non-natives, mustard, Hirschfeldia ancana, and storksbill, Erodium secutarium, were 2 of the most dominant non-native species within this fire scar, or within the plots that we surveyed in the fire scar. And lastly, shrub cover was lowest in the low regeneration class compared with all other classes. And I should mention that there are only native shrubs at this site, so we didn't need to be concerned about non-native shrubs on this landscape. So collectively, what we found is that the lowest regeneration capacity class has the highest cover of non-native grasses and herbs and the lowest cover of shrubs, indicating that they are the best candidates for taking restoration action. We also looked at shrub density, and similarly to shrub cover, we found that shrub density was lowest in the low regeneration capacity class, with 1.5 shrubs per meter squared. And the highest regeneration capacity class had twice as many shrubs. I've included pictures of the four categories, regeneration categories in the field, so you can appreciate the difference in grass and shrub cover across these groups. So here we have a low regeneration capacity plot, and you can see that there's a tremendous amount of avena, which is a non-native grass, in this picture. And as you move across through these photos, you can see that there's fewer and fewer herbaceous and grassy material. So taken together, these findings support the ability of the PREP tool to identify areas of the lowest regeneration capacity across the Powerhouse fire. So these areas are good candidates for future shrub restoration. The second part of the project aimed to evaluate the differences in fire response type. So these are our cedars versus our resprouters across the different regeneration categories to see if certain groups, largely we're thinking about cedars here, were less abundant in the degraded habitats. So to do this, we evaluated the relative density of shrub species that regenerate from resprouts, and those can be seen in blue, versus those that are incapable of resprouting and therefore recruit from seed. And so the density of cedars can be seen in orange. So we separated the analysis by vegetation type to take into consideration the potential difference in densities of resprouters and cedars in chamise redshank, so that's the first box here, versus the mixed chaparral, which is the second box here. And so remember that the field sampling was not fully factorial, so plots were not established in every regeneration category for all vegetation types. But nonetheless, we found that functional type, resprouters and cedars, varied with regeneration capacity, such that low and moderate low classes had fewer cedars than resprouters. So you notice that the orange bars are much lower than the blue bars, while the moderate class for chamise chaparral and the high class for mixed chaparral had a more equitable density of these two fire response types. So this finding is consistent with the idea that cedars are more sensitive to factors leading to degradation, like frequent fire, the abundance of non-native species, as well as post-fire drought, than the resprouters that they coexist with. In conclusion, the PREP tool is intended to assist land managers in chaparral-dominated landscapes and to help more systematically select areas for restoration. The findings from the field monitoring support the outputs from the PREP tool and provide evidence that it's possible to predict areas of degradation based on information about repeat fire, drought, and non-natives. The output from the PREP tool can be combined with information on accessibility, ecosystem service hotspots, the locations of threatened and endangered species to help prioritize restoration projects. And lastly, the tool is not constrained to fires solely on the Angeles National Forest. Rather, it can be applied to any recently burned chaparral landscape on National Forest Service land in Southern California. So this includes the Cleveland, San Bernardino, and Los Padres National Forests. And with the amount of fire we've already seen in Southern California this year, I'm very excited that the tool can help us make decisions on where to focus restoration efforts across these vast landscapes. Lastly, the project couldn't have been completed without the financial support from the National Fish and Wildlife Foundation, the Forest Service Pacific Southwest Region, and the Angeles National Forest. And there were many people who provided valuable input into the tool development, including colleagues from Spain who designed the prototype from which the PREP tool was developed. The field verification was carried out through a partnership with UC Riverside, and UCR led the field monitoring and data analysis for the project. So thank you to all, and please contact me if you have any questions.